In the previous video we looked at 2D Cartesian vectors and we saw that a vector in 2D Cartesian space can be expressed as an x component and a y component. Here I'm writing the vector in column form, but we could of course write it in row form, but I'm going to be using column form for the majority of these videos. So we saw we can express a 2D Cartesian vector as an x component and a y component, and we mentioned that by representing a vector in this way in Cartesian space, that there are a number of powerful operations that we can apply to them. Well, in this video we're going to look at two of those operations. We're going to look at vector addition and vector subtraction. Now, whilst they are very basic operations, they are incredibly useful whenever we're working with vectors. And since we're going to work with vectors a huge amount in computer graphics and programming, it follows that any operation that's useful for us when we're working with vectors is going to be useful for us when we're working in computer graphics and programming. So again, in this video we're going to be looking at vector addition and vector subtraction. So let's start out with vector addition. Well, what we mean by vector addition is if we had two vectors or any number of vectors, so let's say we had a vector A, which was x1, y1, and a vector B, which was equal to x2, y2. So we have two vectors. Vector addition is what happens if we take vector A and we add to that vector, vector B. Well, we know when we're dealing with just numbers, dealing with scalars, how we can add two scalars, two numbers together. It's very, very common and learnt from an early age. So for example, 1 plus 5, we all know that that is equal to 6. But what happens when we're adding vectors? Because you see, a vector has more than just a single number. It has a number of components. So how are we going to add those together? Well, actually, it's very simple. There's a very simple rule with vector addition, and that is that we add together the likewise components. So we take the first component of vector A, and we add to that the first component of vector B, and that's going to give us the first component of our resultant vector. We then move on to the second component. We take the second component of vector A, we add that to the second component of vector B, and that's going to give us the second component of the result. If our vectors had more than two components, we'd take the third component of the first vector, add to that the third component of the second vector, and that would give us the third component of the result. So we're always adding together the likewise or similar components. So the first component of the first vector with the first component of the second vector becomes the first component of the result, and so on. So going back to our A plus B, allow me to quickly erase our scalar addition there. So going back to A plus B, this is equal to, well, we know we're adding those two vectors together, so x1, y1 plus x2, y2, and what we've said is that this is equal to adding together the first component of vector 1 to the first component of vector 2, and that's going to give us the first component of the result. So we're going to take the first component of vector 1, that's x1, we're going to add to that the first component of vector 2, that's x2, and that's going to give us the first component of our resultant vector. So it's going to give us the first component of the result. We then move on to the second component. We take the second component of vector 1. We're going to add to that the second component of vector 2. And that's going to give us the second component of the result. So it's really, really simple. In terms of our 2D Cartesian representation of vectors, we add the x components together, we add the y components together. When we add the x components together, that gives us the x component of the result. And when we add the y components together, that gives us the y component of the result. So it's really very simple, especially in our 2D case that only has two components. Now there is a little bit more I want to discuss about the theory, if you will, behind vector addition. The first thing I'd like to mention is going back to volume 1, where we talked about the various algebraic laws, and we saw in volume 1 that when we're adding two, we didn't call them scalars at the time, we called them numbers, but when we're adding two scalars together, for example, if I had s plus r, if these were scalars, we could say s is equal to 6 and r is equal to 4, for example, they're scalars. If we added two scalars together, they're commutative. That's to say, scalar addition is commutative. S plus R is the same as R plus S. We can switch the two components, or rather two numbers in this case, that we're adding together around, and they're going to give us the same result. And we can see that with our numbers, because 6 plus 4 is obviously equal to 4 plus 6, because they both equal 10. Well, it follows, if the way we're adding our vectors together is simply a series of scalar additions, then it follows that vector addition is also commutative. So vector addition, where we have vector A plus vector B, is also commutative, because A plus B is equal to B plus A. So if I was to actually assign numbers to some vectors, let's say A is equal to 1, 2, and B is equal to, I don't know, 5, 6. Well, we can see that A plus B, let's work that out first, which is great because it's going to give us a chance to actually use numbers rather than just variables here to see how our vector addition works. So A plus B is equal to 1, 2 plus 5, 6, which is equal to 1 plus 5 for our first component, which we know is 6, and 2 plus 6 for our second component, which we know is 8. So again, we take the first component of the first vector, we add to that the first component of the second vector, that gives us 1 plus 5, 1 plus 5 is 6, that becomes the first component of the result. Then we take the second component of the first vector, we add to that the second component of the second vector, that gives us 2 plus 6, which is 8, which gives us the second component of the result. So we can see with A plus B, we get 1 plus 5, which gives us 6, and 2 plus 6, which gives us 8. The result is the vector 6, 8. We can take B plus A, and that's going to give us 5, 6 plus 1, 2. So we've switched our two vectors around, we've switched them over. But of course, because our scalar addition is commutative, we know that 5 plus 1, so the first component of our first vector added to the first component of our second vector, 5 plus 1, is the same as 1 plus 5. So this is still going to give us 6. And 6 plus 2, the second component of the first vector, plus the second component of the second, is the same as 2 plus 6. So our second component of the result is still 8. So we can see indeed that A plus B is the same as B plus A. We can switch our vectors over. It's also worth noting that we can, just like numbers, we can add multiple vectors together. So we could have a third vector, let's say vector C, which is equal to, I'm going to say 8 and 2. And we can add multiple vectors together. So we could have A plus B plus C. And just like with adding numbers, if we're dealing solely with addition, then it doesn't actually matter the order that we add these in, and we can add as many as we want together. All that matters is that we add the similar components together. So with A plus B plus C, we'd get, as I refresh my memory of what A was 1, 2, B was 5, 6. So 1, 2 plus 5, 6 plus 8, 2. As long as we add the first components of each of the vectors to get the first component of the result, and the second components of each of the vectors to get the second component of the result, it doesn't matter the order we add them, just in the same way that it doesn't actually matter how we add 1 to 5 to 8, as long as we get the same result. And we know we do, with addition, get the same result. So 1 plus 5 is 6, plus 8 is 14. Of course, we could have said 8 plus 5 is 13, plus 1 is 14, or 8 plus 1 is 9, plus 5 is 14. It doesn't matter the order we add them. Likewise, 2 plus 6 plus 2, that's going to give us 8, plus 2 is 10. So the result is 14, 10. So that's a little bit about how we're dealing with components of the vectors when we're adding them together, and how that relates to some of our algebraic laws that we dealt with back in volume 1, and basically they directly apply to our vectors, because our vector addition here is simply a scalar addition for the first component and a scalar addition for the second component, so it directly applies. I'd also like to talk briefly about how we can represent vector addition graphically in our Cartesian space, because there's actually a very nice property, if you will, of vector addition in the way that it relates to the graphical representation of our vectors. So I'm going to, again, I guess, deal with 1, 2, plus 5, 6, but I'm going to bring up a new whiteboard so that I can have as much space as possible to do this. So we said that A is equal to the vector 1, 2, and that B is equal to the vector 5, 6. And I'm going to draw a nice Cartesian space. Now I'm dealing with positive values here. I think I'm going to actually give myself as much room as possible and focus on the positive quadrant of our Cartesian space. So there's our X. There's our Y, and I'm going to need, say, go up to 8 in X and Y. So make this 4, make this 8. So this will be 2, 6, and then our values in between. Fantastic. So 2 and 6. I won't bother writing all the numbers in. And then approximately the same spacing down here, just to make this as neat as possible. So 4, 8. So 2 and 6. And then our spaces in between. Fantastic. So we know that any vector that we represent in this way using an x component and a y component in 2D Cartesian space can be represented as a directed line segment. And we know that to do that, we simply have a line that can start at any point because our vector is free to float around our Cartesian space. So what if I was to pick on a point, I don't know, I'm going to pick on this point right here to start my vector. So I'm going to pick at 0 in y and 2 in x. And I could draw my vector A. So I can draw my vector A, and to do that I have a line that's going to travel 1 unit in x and 2 units in y. And we saw this in the previous video, how we can represent our vectors as directed line segments. It's going to travel 1 unit in x and 2 units in y, and that means, as I'm going to erase this because I don't want this massive great dot at the start of my vector. Please bear with me a second. There we go. So I'm going to start here. I'm going to move 1 unit in x, 2 units in y. So that means I'm going to be ending right about here. That's going to give me a vector that looks something like this. So this is the graphical representation of our vector A. Now again, it's free to float around our Cartesian space, but I just personally decided I was going to start it here at 2 in x and 0 in y. There was no reason for that. There's nothing in the problem that we're trying to solve, the problem of A plus B, that dictates the start of that. It's just an arbitrary decision, because if I'm going to be drawing it on the whiteboard here, I need to pick some place to start it, and I decided to start it there. So that's where I've started vector A. Now, we also know we have a vector B. It's going to be 5 units in x, 6 units in y. So that could be something that looks, if I started that at the origin, we'd go over to 5 units in x, 6 units in y, and we'd have a vector. Please bear with my straight line drawing abilities. But vector B would look something a bit like this. But we know that vector B is free to float around our Cartesian space. It can sit anywhere in our Cartesian space. So when we're dealing with vector addition, what we can think of is we start at some point in our Cartesian space and we travel vector A first. So we travel so many units in x and so many units in y as dictated by the components of vector A. That is to say, our directed line segment, we start at some point in Cartesian space and then we travel along our directed line segment to the end of that line segment. So that's what we've done when we've got vector A. Then when we add another vector to it, in this case vector B, we start where we left off at the end, in this case of vector A, at the end before our next addition, and then we travel the length of vector B. So starting at the end of vector A, we're going to travel 5 units in x. So starting here, we're going to travel 5 units in x, so we're at 3. That means we're going to travel all the way along here to 8 in x, but we're also travelling 6 units in y, so we're going to be travelling 6 units in y. which is going to take us from 2 up to 8 in y, which means really what we've done is we've started at the end of vector A, and then we've travelled from the end of vector A along the length of our vector B. So because our vectors are free to float around our Cartesian space, we can position them anywhere. We've positioned vector B so that the start of vector B touches the end of vector A. We can then say that our vector addition is the same as travelling along A, then travelling along B. So what this means is if I constructed another vector, it's going to be a little tight just because of the numbers we've used, so we'll use some other examples in a second. But if I constructed another vector that goes from the start of A all the way to the end of vector B, so it's a vector that looks something like this. Now again, very tight just due to the numbers we've used. This is the same as the result of A plus B. Now how can we verify that? Well, we know that A plus B is 1 plus 5, which is 6 for the first component, 2 plus 6, which is 8 for the second component. And this vector is starting here at 2 in x, and it's travelling all the way along to 8 in x. So if it's starting at 2 and travelling to 8, it's travelling 6 units. And it's starting at 0 in y and travelling along to 8 in y. So 0 to 8 is 8 units. So what we can see with vector addition is that if we're adding our vectors together, we can take the graphical representation of each vector. We start with the first vector at some position, any position in our space, because our vectors are free to float around. We then take the next vector that we're adding it to, or rather adding to it, and we take that vector and position it so the start of the vector is at the end of the previous vector. The resultant vector, the vector of A plus B, is the vector that travels from the very start to the very end. And this is very useful to us because it allows us to think about our vector addition in terms of the graphical representation of our vectors. Now again, this particular example is maybe a little unclear just due to the numbers that we've used. So I'm going to erase this really quickly. I'm going to pick on another example that uses 2 vectors just to help this sort of sink in, and then I'm going to show an example that uses more than 2 vectors, and you're going to see that actually it doesn't matter how many vectors we're adding, we can still use the graphical representation to work out the result. So I'm going to erase our values. I'll leave the actual vectors written there, but I'm going to erase the values. And let's go with something that's going to give us more of a distinguished triangle. So I want something that's heavily moving in x with that first. So let's say 4 units in x and only 1 unit in y. And then something that's going to move quite heavily in y for the second. So I'm going to say 2 units in x, but I guess 4 units in y since... Actually, let's go 5 units in y. I'm just obviously making these numbers up off the top of my head, so do bear with me as I try and sort of visualize in my head without actually drawing it what these would look like so that we get something that gives us quite a nice diagram. So we've got 4 units in x and 1 unit in y. Again, we can start anywhere on our Cartesian space. So last time I started at 2 units in x. This time I'm not going to start there. This time I'm going to randomly pick, I don't know, the origin. So I'm going to start at the origin, and our first vector travels 4 units in x and 1 unit in y. So 4 units in x, 1 unit in y is going to give us a vector that looks something like this. Fantastic, and this is our vector A. Now our next vector travels 2 units in x and 5 units in y. Now we said when we're adding these vectors together, we take the second vector and we start that vector at the end of the first vector. So we're going to start right here at 4 units in x, 1 unit in y, and we're going to then draw our next vector. So we're travelling 2 units in x, and we're travelling 5 units in y, so starting at 1, we're travelling 1, 2, 3, 4, 5, up to here in 6. So this is going to be our vector B. And we said the resultant vector is the same as the vector that starts at the very beginning and travels to the very end of the combination of our vectors. So it's going to be a vector that starts here, in this case at the origin, and travels up right here to the end of B. So this vector is A plus B. Now what I want to do, I'm actually going to use our diagram in this case to get the components of this vector, and then we're going to check to make sure that those components do indeed match with the true component-based vector addition. So in x, we're starting at 0 here in x, and we're going over to 6 in x. And in y, we're starting at 0 in y, and we're going up to 6 in y. So our resultant vector is 6, 6, that's a plus b. And we can see if we took 4 and added 2 to 4, we'd get 6. And if we took 1 and added 5 to 1, we'd get 6. Fantastic. So in terms of the components, we simply add the first components together to get the first component of the result, and we add the second components together to get the second component of the result. In terms of our graphical representation, we take our first vector, and then we position our second vector so it starts at the end of the first. The vector that runs from the very beginning to the very end of that chain of vectors is our result. So here is our component-based representation, and here is our graphical representation, and they are one and the same, they're interchangeable. So I mentioned a second ago that we're also going to look at an example that uses more than just 2 vectors, it uses 3 vectors. It's pretty much going to be the exact same thing. So we've already seen a component-based example of adding together 3 vectors. So let's erase this. I'm going to erase this so we have room to write another vector. But let's see if our graphical representation still works for 3 vectors. So we've got A, we've got B. I'm going to make B not travel quite as far in Y, so maybe 2 units in Y. And I'm going to make B travel a little bit further in X, so maybe 3 units in X. And then C is going to travel 1 unit in X, and I don't know, maybe 4 units in Y. So we've got our 3 vectors, and what I want to find is the result of A plus B plus C. So we're going to start out in this case with vector A, and I'm going to start this at the origin just so I have enough space. So I'm going to move from the origin along the direction of vector A, so that's 4 units in X, and then up 1 unit in Y, so it's going to take me to here. So this is vector A. We're then, from the end of vector A, going to move in the direction of vector B, since that's the next vector that we're adding. So we started and moved along the direction of vector A. From the end of vector A, we're now moving along the direction of vector B. So we're going to be moving 3 units in X along to 7 in X, and obviously up 2 units in Y, which is going to take us up to 3 in Y. So we're then going to add our new vector B. Then from the end of vector B, we're going to travel in the direction of vector C, because that's the third vector that we're adding. So we're going to be traveling a further unit in X, but up 4 units in Y. So we're going to be traveling up here to 7 in Y. Fantastic. That's vector C. Now we said with the 2 vector example, we go from the very start to the very end of our 2 vector chain. Well, it's the same with no matter how many vectors we're adding. We go from the very start of the chain to the very end of the chain of vectors. So we're going to get a vector that travels up something like this. This is going to be our vector A plus B plus C. And we can use our graphical representation to work out the components of this vector, and then we can compare that against had we added the components together. So we're starting here at the origin at 0, 0, and we're traveling 8 units in X, and we're traveling 7 units in Y. So 8 in X and 7 in Y. We can compare this against our components. 4 plus 3 is 7 plus 1 is 8. Fantastic. And 1 plus 2 is 3 plus 4 is 7. Fantastic. So it doesn't matter how many vectors we have, we simply take our first vector, we position the second vector at the end of it, the third vector at the end of that, and so on, and so on. Then we're going to have a long chain of vectors, and once we've got those vectors, we go from the very start of the chain to the very end of the chain. The vector that joins those 2 points is the result of that vector addition. And again, it doesn't matter where we start in our Cartesian space, because we can think of our vectors as being able to freely float around. If we positioned A somewhere else, then relatively speaking, we still have A in the same direction. B would still touch the end of A, travelling in the same direction. C would still touch the end of B, travelling in the same direction, and that means this result vector is still going to have the same length and travel in the same direction. It's also worth pointing out that we could demonstrate the commutativity, if you will, of our vector addition here by switching. In this case, I could switch C and B around, so we could say A plus C plus B, and we can see in terms of the graphical representation we still get the same result, because if after A, instead of appending vector B, we appended vector C, we'd have moved 1 unit in X and then up 4 units in Y, so from 1 in Y up to 5 in Y. So we'd have moved up to about here. So this is also vector C. You'll notice vector C being free to move around in Cartesian space. It's the same length, it's the same direction as this vector, but it's just now in a different position. It's this time touching the end of vector A. From there, we then travel along the direction of B. So from the end of A plus C, we travel in the direction of B. B is 3 units in X and 2 in Y, so we'd move from 5 in X over to 8 in X. And we'd move from 5 in Y up to 7 in Y. We get a vector that looks something like this. This is vector B, and you notice again, if we went from the start of our chain to the end of our chain, we get the exact same vector. So again, just showing the commutative law as it applies to vector addition. We are free to switch these around, and in terms of the graphical representation, we're still going to get the same end result. So again, the graphical representation of addition and the component representation of vector addition, they are one and the same. They are the exact same thing, they're just a different way of looking at it. Are we adding components, or are we dealing with the graphical representation? So that's dealing with vector addition. That's dealing with vector addition in some depth. Now let's take a turn, or take the time rather, to look at vector subtraction. So for vector subtraction, I think it would be best if I was to bring up a new whiteboard. So I'm going to bring up a new whiteboard. And vector subtraction, logically, if vector addition was A plus B, vector subtraction is going to be A minus B. So A minus B. And if you think right back to when we first introduced vector addition, we said that vector A was equal to a vector with x component x1, y component y1, and vector B was a vector with x component x2 and y component y2. So when we're dealing with vector subtraction, it's very, very similar to vector addition, except for instead of adding our components together, we're going to subtract them. So if we have vector A minus vector B, this is equal to x1, y1 minus x2, y2, which is equal to, so for our first component of the result, we're going to take the first component of the first vector and subtract from that the first component of the second vector. So much like addition, but instead of adding, we're now subtracting. So we're going to have x1 minus x2, and that's going to be the first component of the resultant vector. So again, it's the first component of the first vector minus the first component of the second vector, and that gives us the first component of our result. Likewise, the second component of our first vector minus the second component of our second vector is going to give us the second component of our result. So y1, the second component of our first vector, minus y2, the second component of our second vector, gives us the second component of the result. And again, because this directly correlates to scalar subtraction, just simple numerical subtraction, which we know is not commutative, the same is true with vector subtraction. A minus B is not equal to B minus A. And again, we can see this with simple examples. If I was to say that A is equal to the vector 1, 2, and B is equal to the vector, let's say this is equal to the vector 3, 1, we can see this if we were to work out a minus b is equal to, and again the order here is important, so it's equal to a, which is 1, 2, minus b, which is 3, 1, which is equal to, for our first component in the result, we take the first component of the first vector, subtract from that the first component of the second vector, so we're going to get 1 minus 3. For the second component of our result, we're going to take the second component of the first vector and subtract from that the second component of the second vector. That's going to give us 2 minus 1. So our resultant vector, 1 minus 3 is a negative 2, 2 minus 1 is 1. So a minus b is equal to negative 2, 1. However, let's work out what b minus a equals. So b minus a is equal to b first, so 3, 1, minus a, so a is 1, 2. So again, how are we going to work this out? Well, we take the first component of the first vector and subtract from that the first component of the second vector. That gives us the first component of the result. So 3 minus 1 is going to be the first component of our result. Then for the second component, we take the second component of the first vector and subtract from that the second component of the second vector. So 1 minus 2, and that gives us the second component of our result. That means our resultant vector is going to be 3 minus 1, which is a positive 2, and 1 minus 2, which is a negative 1. You'll notice these two vectors are completely different. This vector is minus 2, then 1. This vector is 2, then minus 1. In the previous video, we looked at vector equality, and we said for two vectors to be equal, the x components needed to be equal. Well, minus 2 does not equal positive 2. And the y components needed to be equal. Well, 1 does not equal minus 1. Therefore, these two vectors are not equal, and therefore we know that the commutative law does not hold here, because a minus b does not equal b minus a. So that's just like normal subtraction of scalar values. When we subtract vectors, the order is important. So just as when we're dealing with vector addition and numerical addition, and just as when we're dealing with numerical subtraction, we can, of course, subtract more than one vector. So we could introduce a third vector. Let's introduce a vector c. And I'm going to say vector c is equal to, I'm going to say 4 and, I don't know, minus 2, let's say. And we could have a minus b minus c. Now again, the order is important because subtraction is not commutative, but we could have a minus b minus c. So a, if you recall, is equal to, there we go, is equal to 1 in x, 2 in y. So it's equal to 1 in x, 2 in y, minus b is equal to 3 in x, 1 in y. So 3 in x, 1 in y. And c is equal to 4 in x and minus 2 in y. So just like with our vector addition, we're going to, for our first component of the result, we're going to take the first component of the first vector. We're going to, because we're subtracting here, we're going to subtract the first component of the second vector, so 1 minus 3. And then we're going to subtract the first component of the third vector, so minus 4. Likewise, for our second component of the result, we take the second component of the first vector, 2. We're going to subtract from that the second component of the second vector, 1. And then subtract from that the second component of the third vector. So we're going to subtract minus 2. That means we're going to add 2. That means our result is going to be 1. Minus 3 is minus 2. Minus 4 is minus 6. Then 2 minus 1 is 1. Plus 2 is 3. So the resultant vector is minus 6 in x and 3 in y. Now you'll notice when I was combining these values together, it was exactly the same as when we combine numbers, when we looked at the order of operations. And that is to say, because we didn't have parentheses to tell us otherwise, we work from left to right. So we started at the left, we then worked from left to right. We first started with 1, then we subtracted 3 from that to find the value minus 2, and then continuing on left to right, we subtracted minus 4 from that to get the value minus 6. So it's just like numerical subtraction and addition in that way, in as much as when we're adding or subtracting multiple different vectors together, we're going to, unless there are parentheses to tell us otherwise, we're going to be working from left to right, because the first component of our result is just the same as a numerical addition or subtraction of the first components of each of the vectors that we're adding or subtracting. So all the rules that you'd usually apply to numerical addition and subtraction obviously apply here, and that is to say we work from left to right. And that is important because we can add and subtract vectors in various combinations. We'll take a look at that in a second. But before I get too far ahead of myself, we saw how vector addition can be represented graphically. Well, I'd now like to take a look at how vector subtraction can be represented graphically. In order to do that, I think I'm going to jump back to our previous whiteboard, which we have here. And I think what I'm going to do is erase the diagram on our Cartesian axes, but leave the axes in place since they've worked out quite nicely for us up until this point. So I'm going to erase the diagram but leave our Cartesian axes there. And I'm going to erase some of the notes that we have scattered around. So I'm going to erase this. And let's erase this. And for now, I'm going to get rid of C. And I guess we can leave the values that we've got in here. We can work with those values. So this is vector A, it's 4 units in X, 1 unit in Y. This is vector B, it's 3 units in X, 2 units in Y. And I'm going to take A and I want to subtract B from A. So what is this equal to? Well, we know how we can do this in terms of components. We take 4 in X and subtract 3 from it, which would be 4 minus 3 gives us 1. And then for the second component, we take 1 and subtract 2 from it. 1 minus 2 gives us negative 2. However, let's look at how we can represent this graphically. So again, we could start anywhere in our Cartesian space, and what we're going to do is we're going to travel the length of A, because if we take a look at just A here, that's all we have. We just have A. There's nothing telling us that we have a negative A, or there's nothing indicating anything other than the fact that we have A. So we're going to start from some point in our Cartesian space, and we're going to travel the length of A. Now, in order to do that, what I'm going to do, I think would be the best bet, is to start at the origin, just as a place to start. Actually, no, just to make this even more clear, because I may need some space, I'm going to start at 2. 2. Again, this is an arbitrary decision. I'm just trying to visualize this in my head, how this is going to turn out at the end, just to give me enough space to sort of draw this clearly. But again, it doesn't matter where in our Cartesian space we start, because our vectors are free to float around. So the relative difference between these vectors is going to be the same no matter where in our Cartesian space we start. So I've arbitrarily chosen a position of 2, 2, that's 2 in X, 2 in Y, to start our graphical representation from. And the first thing we're going to do is travel the length of A. So that means we're going to be traveling 4 units in X and 1 unit in Y. So we're going to be starting at 2, 2, and we're going to be traveling, and that's a little bit off, so that's better. Traveling along the length of A. And that's because, again, we just have A here. We have no negative in front of A, it's just A. Once we get to the end of A, if we think back to our vector addition, if we had A plus B, we said that we'd start at the end of A, and then, because it's plus, we'd travel along the length of B. So if it was A plus B, vector addition, once we got to the end of A here, we'd travel along the length of B. So we travel 3 units in X, so 1, 2, 3, and 2 units in Y. So that would be, we are currently at 3 in y, so we travel up to 5 in y. So again, this is if we were adding. That's a really bad line. That's a little bit better. We'd start at the end of A, and we'd travel along the length of B. That's if we were adding these together. But we're not adding, we are subtracting. So what effect is this going to have on the way that we move along the vector B? Well, if we're subtracting a vector, instead of traveling along the vector B, we actually travel in the opposite direction. Now we're going to see why that's the case a little bit later when we're multiplying vectors by a scalar value, because really this is the same as saying multiply by a -1, just in the same way as if we had 2 minus 2 is the same as 2 plus -1 times a positive 2. But again, I don't want to get into too much detail on that now, because this is something we're going to cover in a later video. But what I do want to say is, because it's negative, it's effectively we're traveling in the opposite direction. So instead of traveling in the direction of B, we're actually going to be traveling in the opposite direction, in the direction of negative B, if you will. Now again, these vectors are free to move around our Cartesian space. So if we want to travel in the opposite direction of B, if this is B, and we don't want to travel from the start to the end, we actually want to travel from the end to the start. What that means is when we're positioning our vector B in our Cartesian space, I want to position the end of vector B to touch where we've currently got to, because we've travelled along the length of A, and now we're going to be travelling back along the length of B. So that means if we've got to this point here, the end of A, and we're starting at this point on vector B and then travelling along it, this point on vector B, this end point, needs to touch the end point of our vector A. So starting here, our vector B is actually going to be travelling so that its end point touches this point in space. Now again, we're travelling 3 units in x, 2 units in y. So to reach this point, we must travel backwards 3 units in x. So we're going to go minus 3 units in x. That takes us from 6 back to 5, 4, 3. And we're going to be travelling backwards 2 units in y, so from 3 down 2 units to 1. So we're going to have a vector that looks like this, would be our vector B, but instead of travelling along vector B from start to end, because we're subtracting, we're travelling in the opposite direction from end to start. The result of this chain of vectors, of course, this guy out here isn't part of our chain of vectors, but I'm going to leave him there for comparison because vector B is the same as vector B here. It's the same vector, it's just a different position, but we know position doesn't have anything to do with our vector. So it's the same vector. We take our chain of vectors, and again we go from the very start to the very end. But again, we've walked along, if you think about it, walked along the length of A, then we've walked down the length of B in the opposite direction. So where is our very end? It's here at the start of B. So the resultant vector that goes from the start of our chain, and then we move along our chain back down here to the end of our chain, that vector is A minus B. So we can work out the components of that vector. We can see that we start here at 2 in x, 2 in y, and then we end up at 3 in x, but 1 in y. So if we start at 2 in x and end up at 3 in x, that means we've moved 1 unit in x. If we start at 2 in y and end up at 1 in y, that means we've moved a negative 1 in y. If we compare this now to our components, 4 minus 3 is 1. 1 minus 2 is negative 1. So whether we're using our components or whether we're using a graphical representation, we can still do vector subtraction. The only catch, the only difference between vector subtraction and vector addition in terms of our graphical representation is that we don't travel from the start of a vector we're subtracting to the end. We travel in the opposite direction. Now again, this is going to become more apparent when we deal with scalar multiplication of a vector, but for now just think about this as, because we're subtracting, we travel in the opposite direction. So we travel from the end of the vector down to the start. Because of that, wherever we've got to before the point where we subtract a vector, because of course we could have c plus a and then minus b, wherever we've got to before the point where we subtract a vector, at that point, when we're subtracting a vector, we position the endpoint of that vector at the point that we've got to. So in this case, we travelled along the length of a, and we'd got to this point right here. At that point, because we are subtracting b, we then place the end of vector b there, travelled in the opposite direction down the length of vector b, and that gave us our endpoint, because that was the end of our subtraction in this case. The result from the start of our chain to the end of our chain, that is the result vector. So once again, when we're subtracting, we travel in the opposite direction along the length of our vector. Now I do want to sort of help get this to sink in, so what I'm going to do is I'm going to erase some of this. But to save on time, I'm going to leave our vector a there, I'm going to leave our vector b there, but I'm going to change our equation. Do bear with me just a second. So I'm going to change our equation to a plus b. Well, we know that a plus b would give us the result that goes, as my line is a little bit dodgy there, from the start of a to the end of b. We've already seen that earlier in this video. Well, I'm going to introduce a third vector, a vector c, which is going to have 4 units in x. Actually, I don't really want to go 4 units in x. I want to go 1 unit in x and 4 units in y. Again, I'm trying to visualize this in my head before drawing it on the whiteboard so we get a nice clear diagram. And the equation I want to equate is a plus b minus c. So what is that equal to? Again, this is just to help hone in the fact that when we're subtracting, we travel in the opposite direction along a vector, but it's based on where we've got to up until that point. So we start with a, and from any point in our Cartesian space, we can start from a and travel along the length of a, and we've done that here, and that's got us to this point in our Cartesian space. The next part of our equation, working from left to right, is to add b. So we're adding b. That means we start at the end of a and we travel in the direction of b. We've already done that, and that's taken us to this point right here. Now that we've got to this point, we've just added b. So we started with a, we've added b, we've now got to this point right here. We're now subtracting c. That means from this point, we need to travel in the opposite direction of c. That means we need to place c, if you will, such that the end of c touches the end of b. So c would move 1 unit in x and 4 units in y. So it would move over approximately 1 unit in x, and it would move up 4 units in y. So 1, 2, 3. Something like this would be if we were adding c. That's the direction we travel, but we're traveling in the opposite direction. So the end of c is going to touch here, and we're going to travel minus 1 in x, so that's down to about here, and we're going to be traveling minus 4 in y, so 1, 2, 3, 4, down to about here is going to be giving us c. So again, this is vector c, it's the same vector as we have here, but because we are subtracting it, we place the end of the vector at the point that we'd got to, and that's this point here, and we travel in the opposite direction down the vector. The result of a plus c minus b, again, is the start of our chain to the end of our chain. So it's going to be this vector that comes across, as I struggle to draw a straight line here, please, I do apologize for that awful straight line. It's going to be a plus b minus c. So we can see in terms of our graphical representation, we start at 2 in x, we end at 8 in x. That's going to be 6 units in x that we've travelled. We start at 2 in y, we end at 1 in y. So that's going to be 1 unit, or rather minus 1 unit in y that we've travelled. We can see this if we took 4. So a plus b, so 4 plus 3 is 7, minus c. So 4 plus 3, 7, minus 1 is 6. And a plus b minus c, 1 plus 2 is 3, minus 4 is minus 1. So again, the graphical representation and the component representation, they are one and the same. They are interchangeable. It's just a different way of thinking about the exact same problem. So now that we've seen both vector addition and vector subtraction and combinations of both addition and subtraction in terms of their components and in terms of their graphical representation, I'd now like for you guys to work through just a few questions on your own. So I'm going to set some questions here on the whiteboard. I'm then going to give you the chance to pause the video, work through these questions on your own. Once you have a solution, or if you get stuck, you can unpause the video, and then I will work through the answer here on the whiteboard. Okay, so in order to set some questions, I am going to need a little bit of space on the whiteboard. I also am going to be making use of my Cartesian space here in a little bit. So just to prepare, I'm going to clear this away, just so that we can make use of that. I can leave our other notes and scribblings up here. I'm also going to bring up a new layer just so that with each question I can hide out the layer, and that's going to immediately clear away this portion of the whiteboard for us. So scrolling down, fantastic, question 1. So with question 1, I'd like you to add together these two vectors. So the first vector is 1, 2. I'd like you to add to that the vector 2, 4. So I'd like you to find the result of that vector addition. I'd also like you to find it both in terms of the components and in terms of the graphical representation, just to give you a chance of working with both different methods. So once again, add together the vector 1, 2 to the vector 2, 4, and do that both in terms of their components and in terms of a graphical representation. You can now go ahead and pause the video. When we come back, I'm going to work through a solution here on the whiteboard. Okay, welcome back everyone. So let's work through our component solution first. So quite a simple vector addition we have here. So we know when we're adding two vectors together, we take the first component of the first vector, we add the first component of the second vector, and that's going to give us the first component of the result. So we're going to take 1, we're going to add 2 to that, and it's going to give us the first component of the result. For the second component of our result, we're going to take the second component of the first vector, which is 2. We're going to add to that the second component of our second vector, which is 4, and that's going to give us the second component of the result. So once again, we've seen this many times now, but for the first component of the result, we're taking the first components of our vectors and we're adding them together. For the second component of our result, we're taking the second components of our vectors and we're adding them together. So this is going to give us, in component form, we're going to get 1 plus 2 is 3, and 2 plus 4 is 6. Okay, so this is the answer for 1, 2 plus 2, 4. It's the vector 3, 6. But I'd also like to see this in terms of their graphical representation as well. So I'm going to scroll on up just enough so that we can actually squeeze this in, and we should be able to squeeze it in. Fantastic. So I'm going to start at the origin. Of course, you could start anywhere in Cartesian space. What matters is the relative difference between these vectors, how these vectors connect together, and not where they start in Cartesian space. But I am going to start at the origin just so I have enough room to actually fit this in here. So our first vector, if we start at the origin, is going to travel 1 unit in x, 2 units in y, and that means we're going to travel along that vector right there. Then, from the end of this vector, we're then going to travel along the length of our second vector, which is another 2 units in x, and up 4 units in y, so 2, 4, up to here. Fantastic. And we know, of course, that in the graphical representation, our result vector is going to start from the start of our chain of vectors and travel to the end of our chain of vectors. Now, on the Wacom, this might be a little hard for me to draw neatly. It's going to look something like this, is the result vector. We can see this vector here starts at the origin and travels 3 units in x. So we have 3 in x, and we've started at the origin and traveled 6 units in y. So we have 6 in y. So both the graphical representation, which is a little bit squeezed in there, and our component representation, the result is 3, 6. Fantastic. So that's question 1. I'm going to hide out that layer, bring up a new layer here for question 2. So question 2, I guess let's practice some subtraction now. So I'd like you to take the vector 10, 0, and subtract from that the vector 5, 5. So again, this is both in terms of components and in terms of their graphical representation. So that's the vector 10, 0, subtract from that the vector 5, 5. When we come back, I'll work through the solution on the whiteboard. Okay, welcome back everyone. So I'm going to start with our component representation again, and then we'll look at the graphical representation. So with our component representation, we're going to take for the first component of our result, the first component of the first vector, which is 10, and we're going to subtract from that the first component of our second vector, which is 5. For the second component of our result, we take the second component of our first vector, and we subtract from that the second component of our second vector, which is going to give us, for the first component, 10 minus 5 is 5. For the second component, 0 minus 5 is a negative 5. Fantastic. So we can now look at this in terms of a graphical representation. Now, my graph here, I can extend this up to 10 without any issues. In y, we may struggle to fit it all in, but we'll see. I mean, we may just have to imagine where on this graph it goes to, as these are quite big values. So I'm going to start out, and knowing where the resultant vector is going to go, I'm actually going to start this at 5 in y and 0 in x. Again, we can start our vectors anywhere. It's an arbitrary decision, but I'm going to start at 5 in y and 0 in x in the hope that everything will fit nicely with our diagram here. And the first thing we're going to do is travel along the length of our first vector. There's nothing here to indicate that this is negative. It's simply the vector 10, 0. So that means we're going to travel 10 units in x and nothing in y, which means we're going to travel over to here. So 10 units in x and nothing in y. And that's our first vector. We're then going to be traveling along our second vector from the end of our first vector, but because we have a minus here, we're going to be traveling in the opposite direction. That is to say, the end of our vector needs to touch the end of where we've got to. So starting here, we're going to be traveling minus 5 units in x and minus 5 units in y. So we've traveled backwards 5 units in x, backwards 5 units in y, down to this point here. But of course, the vector is actually this vector. It's 5 units in x, 5 units in y. It's just we're traveling down the opposite direction. That means the resultant vector, something like this, is going to be traveling from the start of our vector chain to the end of our vector chain, and this is going to give us 1, 2, 3, 4, 5 units in x, and starting at 5, minus 1, minus 2, minus 3, minus 4, minus 5 units in y. So that's a positive 5 in x and minus 5 in y. So again, there's the component representation, and here is the graphical representation. Fantastic. So I'm going to hide this out. I'm going to bring up a new layer. And now that we're comfortable, hopefully, with both the graphical representation and the component representation, I'm now just going to focus on the component representation of our vectors. So in this case, for question 3, I'd like you to equate the following vector addition. So we're going to have the vector 3, 2, and then add to that the vector, I guess 4, 0 will work quite nicely, and then add to that the vector 5, minus 2. And I'd like you simply to work this out using the component representation. Of course, if you feel that you'd like to put in the extra little bit of time and do this graphically just to help sink that in, then that's great. But I'm only going to be working through the answer in terms of the components here on the whiteboard. So go ahead and pause the video. When we come back, I'm going to work through the answer here on the whiteboard. Okay, welcome back everyone. So we're adding together these three vectors. So our result vector, we know for the first component of the result, we're working from left to right. So we start with 3. We're going to add to that 4. And then we're going to add to that 5. Because for the first component of the result, we're dealing with the first components of our vectors. For the second component of the result, we're dealing with the second components of our vectors. So working left to right, we're going to take 2, we're going to add to that 0, and then we're going to add to that minus 2, which means we're going to subtract 2. So this means the result is going to be 3 plus 4 is 7, plus 5 is 12, and then 2 plus 0 is 2, minus 2 is 0. So our resultant vector is 12, 0. Fantastic. So let's look at one last example, so hopefully all of this is sinking in. So question 4, again, we're going to be dealing with multiple vectors. This is going to combine both subtraction and addition here, so just take your time and be careful with this one. So we're starting out with the vector 4, 0. We're going to subtract from that the vector 0, 4. Then subtract the vector 1, 1. Then add the vector 2, 3. So if you can find the result of that, again, I'm just going to be working through the answer in terms of components, but if you feel like drawing this in terms of the graphical representation, then it will be some great extra practice for you. Okay, welcome back everyone. So again, the key here is that we work from left to right. So our result vector, in our first component, we're dealing with the first components of our vectors, and we're going to work left to right. So we're going to take 4 minus 0 minus 1 plus 2. So 4 minus 0 minus 1 plus 2. Again, left to right for the first component of our result. It's the first component of our vectors. The second component of our result is going to be the second component of our vectors, again working left to right. So 0 minus 4 minus 1 plus 3. So 0 minus 4 minus 1 plus 3. That's going to give us as a result 4 minus 0 is 4, minus 1 is 3, plus 2 is 5. 0 minus 4 is minus 4, minus 1 is minus 5, plus 3 is minus 2. So the result is 5 in x and minus 2 in y, and that is going to conclude all of the questions in this video. So to recap, we've seen that with vector addition, we simply add all of the corresponding components of our vectors. So with vector addition, we simply add all the first components to get the first component of the result, all the second components to get the second component of the result. So with vector addition, we simply add all the corresponding components. With vector subtraction, we subtract the corresponding components. Like with adding and subtracting numbers or scalars, addition is commutative, subtraction is not commutative, and again we work from left to right. So if there are no parentheses telling us otherwise, we work from left to right. We've seen how we can add and subtract vectors both in terms of their components, but we've also taken a look at how we can do that graphically as well. They're both the same thing, they're both interchangeable. It's just nice to know, if we're dealing with components, what's actually going on in terms of the graphical representation of our vectors, because that's quite useful to know, and it can come in handy when you're dealing with solving problems. So that's going to conclude this video where we looked at 2D, vector addition and vector subtraction. Thanks a lot for listening, everyone.